Let us talk about some boundary points first. So the maximum deviation, this kf into mtk, mtk can be at max mp and at least minus mp. So whatever is the sync corresponding to the maximum and minimum deviation, we have omega c minus kfmp and omega c plus kfmp, because you know this mtk can have a value of mp and minus mp at max and at min. And similarly, for a general value, we have omega c plus kf into mtk. Whatever is the value of mtk, we will substitute it here, and this could be anywhere between these two extremes. Now, let us further talk about the width of these sinks that we have got here. We already know that sink is already infinite in extent. So since it is infinite in extent, we can see that the bandwidth of this signal is infinite, and which is true theoretically. But again, practically speaking, most of the energy of this sink function can be assumed to be concentrated within certain lobe of the central frequency. So if we see all of these sync functions, we can say that the bandwidth that is around the center point, if we take 8 pi b on both the sides, that is from here to here, if the distance is 8 pi b, or you can say that the half distance is 4 pi b radians per second, then your most of the energy will be concentrated in this particular region. So practically speaking, for this particular sync function, you take this 8 pi b gap and you can neglect all of the other things which go up to infinity. Similarly, you can do the same thing for all of these sync functions. So you will get a practical Fourier transform for this particular thing. So from this diagram, we define the bandwidth. The complete bandwidth of this complete thing is theoretically infinite, but if you take this practical thing into consideration, that energy is concentrated here and here. So I note this point and I note this point. This point will be omega c minus kfmp. This central point will be omega c minus kfmp. We already know this is because of modulation theorem, and around that, if you go into this negative direction, you have minus of 4 pi b. Half of this 8 pi b is 4 pi b. So you have this particular extreme limit to the left, where most of your practical energy will be stored. And similarly, on for this particular point, you have omega c plus kfmp plus 4 pi b, and this is the region between which your complete spectrum will be there for this particular signal practically. So the difference between these two will give me bandwidth. So we have got this bandwidth as 2 kfmp plus 8 pi b, right? So you see here you have this thing and you have this thing. If you take the difference, this will be kf mp, and this will be added here, so this will be 2 kf mp, and 4 pi b will become 8 pi b. So this is the bandwidth that you have got here. And also the frequency deviation that we can have here, delta omega, is kf into mp. Why? Because the maximum value of this signal could be mp, so the frequency of the carrier signal, the maximum extent up to which it can go is omega c plus kf mp or omega c minus kf mp. So from the central frequency, the maximum extent up to which this can go, the instantaneous frequency can go, is delta omega, and that is kf into mp radians per second. So we have noted these 2 points from the spectrum. Now if we want to define this bandwidth in hertz, then we have this bandwidth of fm is equal to 2 kf mp plus 8 pi b, and simply we will divide it by 2 pi, so we will get the required bandwidth in hertz. Or if you want to develop this formula in terms of this frequency deviation, instead of this delta omega, if you take delta f, you will also divide this by 2 pi. So this formula can be alternatively written as bandwidth of fm is equal to twice of delta f plus 2b. So this is the formula that we have received from this diagram. Now this is valid in all cases, whether it is NBFM or whether it is WBFM or any case between them. So this formula is valid for all of the possible cases. Now let us apply this formula to NBFM case, because we have already studied the NBFM case and we already know that for NBFM the bandwidth will be 2b from the previous video. So for NBFM, we already know that this frequency deviation will be very less. So let frequency deviation tend to 0, and bandwidth of FM, we already know that this is 2b, but from here it comes out to be 4b. So a good thing would be to drop this 2. Why? Because for NBFM case, we were very sure that the bandwidth has to be 2b. And here if you put delta f equal to 0, you will get the bandwidth of fm is equal to 4b, but ideally it should be 2b. So this thing comes because we have taken certain area around this. So different authors take different areas around this sync function. Some people take it from this point to this point, some people defined it from half power, and there are various other criteria. So this width can be changed accordingly. So to match with our NBFM's observation, instead of taking this as 4b for delta f is equal to 0, we take it as only 2b. That is, we drop this 2, so this 2 will be multiplied and this will become 2b. Right. So that is why this bandwidth of FM can be defined as 2 delta F plus B instead of this 2B, because we had this from our NBFM's results, and this would hardly change our spectrum or bandwidth in any sense, because practically speaking, even if you take this formula, the bandwidth would be, the maximum power would be concentrated between these 2 points instead of these 2 points. Right. So this is also a equally good formula, and this formula is known by Carson's rule, and this formula is in hertz because delta f is there. If you define this formula in terms of delta omega, that would not be in hertz, it would be in radians per second. So this is Carson's rule. Now another thing is, if you want to measure how much frequency deviation is there with respect to the bandwidth, so you define one thing which is called as deviation ratio. Deviation ratio beta is equal to delta f by b. So if delta f is very less as compared to b, as in the case of NBFM, so this beta will go to 0, and you can see that for beta equal to 0, if you write this formula, or if you write this Carson's rule in terms of beta, your bandwidth of FM will become equal to 2b plus 2b bracket beta plus 1. So if beta is 0, the bandwidth of FM will become 2b only, and if beta has non-zero value, you will get the values accordingly. So this deviation ratio is also there. And for tone modulation, that is modulation with sinusoidal signals, it is called as not your deviation ratio. Similar to amplitude modulation case, it is called as modulation index. So modulation index terminology is valid when we modulate our carrier signal by using a message signal which is sinusoidal in nature. So in that case only we will call it modulation index. Otherwise it is deviation ratio. So this is the final formula. This is also the Carson's rule, but it is not in terms of beta, that is deviation ratio, and this is your Carson's rule in terms of deviation ratio.